This is the second part of my lecture on sampling, in which I'm going to talk about how we can make inferences from measurements of a sample. As we said in the previous part of this lecture, usually we don't have the luxury of measuring the whole population, we just have a small sample to deal with. So now we want to think about what inferences we can make about the whole population from just one sample. In particular, we want to think what is our best estimate of the population mean based on our sample, and what is our best estimate of the population standard deviation based on our sample. Here are the formulae that we would use for the sample mean and the population mean. They both look exactly the same. They sum up all the measurements, and the sample mean divides by the number in the sample, and the population mean divides by the number in the population. Of course, there will be many more measurements in the population than in the sample, so we end up with slightly different results, as we've observed before. The population mean and the sample mean may be slightly different. The difference is what we call the sampling error. So the problem is that the population mean can only be calculated if we've got the whole population available, and very often that isn't just possible. So if we've only got the sample available, we have to use the sample mean as our best estimate of the population mean. In other words, we can say that MP, the population mean, is approximately equal to MS, the sample mean. We can measure the sample mean. We can't measure the population mean because we don't have the population, but we use our sample mean as our best estimate of it. So, as we observed in the previous section, when we looked at the illustration using ages of patients, we saw that the sample mean MS is an unbiased estimate of the population mean MP. Unbiased means that it may be a bit smaller than the population mean or a bit larger than the population mean, but on average it's the same as the population mean. It's not biased to be always bigger or always smaller. It averages out to be the same. The larger the sample size, the better it will estimate the population mean. So as long as our sample is not too small, the sample mean is a good estimate of the population mean. That's fair enough, but what about the standard deviation? Well, the formula for the standard deviation is based on calculating the variance first of all. And here we look at the formula for the sample variance and the population variance, and they're very similar. The differences are that the sample variance subtracts the sample mean from all the measurements, and the population variance subtracts the population mean from all of the measurements. Apart from that, the formulae are the same. So the population variance is taken about the population mean, but we don't know the population mean. The sample variance is taken about the sample mean, which we do know, and we've already observed it may be slightly different to the population mean. Now, if we think about it, the sample measurements xi in the calculation of the sample variance will be usually closer to the sample mean MS than to the population mean MP, because the sample mean is derived from those measurements to be the average of those measurements. So on average the individual measurements xi will be closer to the mean calculated from those measurements than they would be to the population mean, which we don't know. So the sample variance Vs is going to be less than the population variance Vp, because the differences that we're squaring for the sample variance are going to be smaller than the differences we're squaring for the population variance. That means that the sample standard deviation is always going to be an underestimate of the population standard deviation. The sample standard deviation is expected to be smaller than the population standard deviation, simply because the measurements are going to be closer to its own mean than to the population mean. This is a more formal explanation of why that happens. It's exactly the effect that we looked at in the last part of this lecture when we observed that it happened in the example that I showed you of patient ages. So what can we do about this? Here we've got the formula for the sample variance, calculating the difference of all the samples from the sample mean and dividing by the number in the sample. From that we can calculate the sample standard deviation. Now if all we've got to go on is the sample, the best way we can calculate the population standard deviation is to use MS instead of MP. The proper formula for the population variance would have MP here, but we don't know that. We have to substitute MS. And it turns out that a way of allowing for that is to substitute NS with NS minus 1 in the denominator of this equation. So using MS instead of MP introduces a bias, as we've just observed, and we can compensate for that by using n minus 1 instead of n in the denominator. So that gives us a different formula for calculating standard deviation, with n replaced by n minus 1. If we look at this formula, we can see that if we take the formula for Vs, which has got an ns in the denominator, and multiply by ns over ns minus 1, that gives the formula with an ns minus 1 in the denominator, which is our formula for Vp. So if we know the sample variance Vs, we can multiply it by ns over ns minus 1 and get a best approximation to the population variance Vp. Alternatively, if we're working with standard deviation, which is just the square root of the variance, then we can multiply the sample standard deviation SS by the square root of ns over ns minus 1, and that gives us the best estimate of the population standard deviation SP. So this factor ns over ns minus 1 is a correction factor, and it's called Bettles correction, and it's a way of allowing for the fact that the standard deviation or the variance of a sample underestimates the correct value for the population. Note that ns over ns minus 1 is going to be quite close to 1 if ns is large. The bigger ns is, the smaller the difference between ns and ns minus 1, and so in that case Bettles correction becomes very close to 1 and SP and SS become almost equal. So this correction really only matters when the sample size ns is relatively small. Let's just see how that can be put into practice. Remember the example of the age of our patients that we looked at in the last part of this lecture. Remember we had a standard deviation of the whole population of 10.4, whereas our sample of 20 gave a sample standard deviation of 10.1, and a sample size of 10 gave 9.7, and samples of 5 gave 9.1. That illustrated the fact that we underestimated the true population standard deviation. Now if we apply Bettles correction, which is the square root of n divided by n minus 1, if n is 20, then Bettles correction is the square root of 20 over 19, and if you multiply 10.1 by the square root of 20 over 19, it comes out to 10.4. If you do the same thing with our sample size of 10, Bettles correction is the square root of 10 over 9, which converts our 9.7 into 10.2. Now sample size of 5, the Bettles correction root 5 over 4 converts our 9.1 into 10.2. So you see that all of those samples of size 20, 10 and 5, if we apply the Bettles correction to the sample standard deviation, we get a much better estimate of the population standard deviation. So Bettles correction works in practice. It doesn't give a perfect answer, but is a much better approximation to the true population standard deviation than just using the sample standard deviation on its own. So people often get confused about whether there should be an n or an n-1 in the denominator of these equations. The equation for variance, and hence the equation for standard deviation, either has an n or an n-1 in the denominator. The rules for deciding whether to use n or n-1 depends what you want to do. If you're calculating the population parameters, either mean or standard deviation or variance, from the whole population with a number of samples np in it, so this is assuming that you've got all the population available to you, then you're always going to have np, the number in the population, in the denominator of these equations. If you're calculating the mean, the population mean, I've called mp, other texts may use the symbol mu for that. I've used SP for the standard deviation, other texts may use the letter sigma for that. I've called the variance VP, other texts may use sigma squared. If you want to calculate in Excel, the function for doing the mean is the average, and standard deviation is calculated uses stdevp, and the variance using varp. The p at the end indicates that these are calculating using the population, which is what you might expect in that circumstance. However, if you're calculating the sample parameters from the sample, you have the ns measurements available from the whole of the sample, then as you expect you use ns in the denominator of these equations, and I call the mean ms, where other texts may call it x bar. I've called the sample standard deviation SS, you may see S or SN in other texts, and the variance I've called VS, and other texts may use S squared or SN squared. Now the slightly odd thing here is that the Excel function for standard deviation and variance is still stdevp or varp. The p at the end you might think applies to population, but here we're using it for the sample. You give it all of the sample measurements, ns measurements, and it calculates the standard deviation of that sample in exactly the same way as if you gave it all the population measurements, it would calculate the standard deviation or the variance of the whole of that population. So it works on whatever you give it, the population or the sample. The confusion comes when you want to estimate the population parameters from a sample of size ns. So we have only the sample, but we want to get our best estimate of what the population parameters are. Well, we've already seen that the sample mean is an unbiased estimate of the population mean, so you use exactly the same formula as you would use for calculating the sample mean. The function average calculates the sample mean, and it is the best estimate of the population mean, which I've called MP, and other texts might call mu. But we've already seen that calculating the sample standard deviation is an underestimate of the population standard deviation, so you need to put ns-1 in the denominator of that equation. If you do, you will calculate the population standard deviation. I've called it SP, some texts might call it S, or Sn-1, indicating that there's an n-1 in the denominator. And the Excel function for that, stdev without the p on the end, is the one that has the n-1 in the denominator, and so that's the correct one to use. Similarly, the function var without the p at the end is the one that calculates the variance using the ns-1 in the denominator. So those are the ones to look out for, but the normal calculation is the one with the p at the end. I don't blame you if you feel confused at the end of all that. The literature is somewhat confused as well. The name sample variance is used to mean different things by different people. Some authors use a formula with n in the denominator, just like the one that I've given you for the sample variance Vs, and they call that the sample variance. This is the method that I like, because once you've calculated the sample variance, you apply the Bettles correction to estimate the population variance. That's the method that I'm using in these lectures, and certainly other people in the literature will do the same thing. However, other authors use a formula with n-1 in the denominator, like the one that I've given you for the population variance, but they still call it the sample variance. But they use it as an estimate of the population variance based on the sample. I find that rather confusing, but that is the approach taken by other authors. Yet again, there are others who try to avoid the confusion by using both formulae but giving them different symbols. For example, I've quoted Sn squared for the standard deviation calculated with n in the denominator, and Sn-1 squared with the n-1 in the denominator, and there are authors that use that. And indeed, many calculators will have sigma n and sigma n-1 buttons on them to do either of those calculations. So you won't be the only ones confused if you don't understand exactly which formula you should be using. I hope that I've made it clear my preference there, and I hope that you won't get confused by what other authors might use. Just be aware that this difference exists. The most likely cause for confusion is if you're going to use Excel, because I've been suggesting that you can use Excel for some of these example calculations. But Excel provides two different functions for calculating standard deviation: stdev without a p and stdevp, and corresponding functions for calculating the variance, var and varp. So you really want to be clear which of these to use. Well, it depends what you're doing. If you've got the whole population available and you want to calculate the standard deviation and variance of the whole population, then use stdevp and varp, the ones with the p at the end, as you might expect for population, calculating the population parameters. Those functions use the n form with an n in the denominator, and they calculate the standard deviation of the entire population, assuming that you give them the entire population. That's straightforward. But if you've just got a sample and you want to calculate the standard deviation and variance of the sample, then you still use stdevp and varp, the ones with a p at the end, which is counterintuitive because you're giving it a sample and you want to calculate the standard deviation of the sample. So why do you use the p form? Well, the reason is because you still want the n in the denominator, and the help in Excel unfortunately fails to mention that you can use these functions for just that case. So you will have noticed in previous lectures when I've told you to calculate the variance or the standard deviation with Excel, I've told you to use the p form, because that is what we have been doing, calculating the standard deviation and variance of a sample. If you give it all the sample and use stdevp, it will calculate the standard deviation of the sample. So the other case is when you've got a sample but you want to estimate the standard deviation and variance of the whole population. That is when you use the stdev and the var without the p at the end. Those are the functions which use the n-1 in the denominator. The Excel help is slightly confusing on this point because it says that they estimate the standard deviation and the variance based on a sample, which is true, but it fails to point out that the standard deviation and variance that they give are the best estimates of the population standard deviation and variance. So despite the fact that there isn't a p at the end of these functions, they are estimating the population parameters based on a sample. So I hope that doesn't make it even more confusing, but when you come to use Excel, if you just stop and think what you're doing, if you're calculating based on a population or a sample and that's all you have, use the p form. If you're trying to estimate the population parameters from the sample, use the form without the p. Well, after all that, you may think, does it matter? Well, the difference between the two formulas is this Bettles correction, the square root of n over n minus 1. If the sample size is large, for example if n is greater than 10, then Bettles correction is fairly close to 1. In fact, if n is equal to 10, the Bettles correction is the square root of 10 over 9, which is 1.05, so it only makes a 5% difference. So in practice, if n is more than 10, it really doesn't matter whether you use the n or the n minus 1 form. There's hardly any difference between them. The difference only really matters if n is less than 10. So if you've got small samples, less than 10, then it does matter whether you apply the Bettles correction or not. But with small samples, there's going to be such a large variation between samples anyway, that neither formula is going to be very accurate. They're both only estimates. So probably you shouldn't be trying to estimate the sample standard deviation if you've got fewer than 10 measurements. And there are those who would say that the estimate is too inaccurate anyway, even if you apply the Bettles correction. So the bottom line is, don't lose any sleep over which you use. If the sample size is large, it doesn't matter which you use, and if the sample size is small, you probably shouldn't be using either. So, I hope that's not confused you too much. That's the end of this second part of this lecture on sampling.